The topic of today's talk is a little bit strange. It's not a software engineering talk, definitely, but it talks about a tool that is very interesting for us software engineers, ChatGPT, and I would say large language models in general. So the typical way we look at these models is they can generate code, or they can generate documentation from code. So they are very interesting because they address interesting software engineering tasks. But maybe there is something more beyond these large language models. And there are some recent studies that try to investigate whether there is something more. And this investigation is done sometimes scientifically. Of course, there's a lot of chatting around that. There's a lot of blogs and so on. But for this seminar, I selected a work that I think scientifically is very interesting. So why can there be something more behind large language models? Well, if you look at the machinery at the bottom, at the base of these tools, it takes inspiration from biological neurons, but it does actually more. It simulates the behavior of a neuron, of a set of neurons in a so-called artificial neural network, where, of course, there is an abstraction. The neuron is considered as a computational entity that is connected to other neurons through synapses. And these synapses change, weight, basically the signal that comes from the other neurons. Every neuron generates a signal, which is some frequency signal, and the synapses can increase or decrease the frequency, and then the neuron aggregates it and produces an output signal with some frequency through some, let's say, usually nonlinear transformation. This kind of behavior is implemented in artificial neural networks. And of course, if you have just a few neurons, you don't get much out of it. But if you start having billions or tens of billions of neurons, as happens in the large language models, then the size that you get is not, of course, the same that you have in a biological brain, but it becomes quite comparable. Still, there are orders of magnitudes in between, but there's something that might be compared. And then the question is, okay, we have interesting emerging properties in the human brain, consciousness, just to mention one. Can we have the same emerging properties in an artificial brain? And of course, there's a lot of philosophical and principle discussion about it. As I said, this work tries to take a scientific approach to evaluate these emerging properties. So for this seminar, all the credits go to the author of this work. None of it is mine. I do research on other topics, of course, as you know, software testing, software engineering. The author is Michael, I'm not sure how to pronounce, Kosinski, from Stanford. The title of his paper is Theory of Mind May Have Spontaneously Emerged in Large Language Models. It's not yet published. The one that I present is a preprint taken from arXiv. So first of all, what is the theory of mind? It's the capability that we have as human beings to attribute some mental state to others, to other people, to other humans usually. What do we mean by mental states? For instance, beliefs or desires. These are the kind of attributions that we as humans, thanks to our brain, can make. And this capability is quite important. Of course, in social interactions, the fact that when we interact with somebody else, we can make the assumption that there is a mental state in the other person interacting with us is very important for communication, for empathy. It's also very much related to self-consciousness. If I can believe that somebody else has an internal mental state, then I can also reason about my own internal mental state. For moral judgment, for religious beliefs, all these aspects of the social human life are deeply influenced by this capability of attributing a mental state to other people. And this capability, this theory of mind capability, has been investigated also clinically, because there are diseases that create these functions of this capability. Namely autism, bipolar disorder, schizophrenia, and psychopathy. are all diseases, are all dysfunctions that reduce or even eliminate this capability to attribute a mental state to other people. So the people that suffer from these diseases have always a very hard time in, making this process of attribution of a mental state similar to their own to other people, which has a number of consequences in their life. If we look at animals, and in particular the most evolved ones like great apes, they lack this ability completely. According to all the tests that were done, they don't have this capability of attributing a mental state to other animals or people. And this capability was shown to be highly correlated with the language. In particular, language is very important to acquire this capability. And when there are people who acquire language abilities late, because, for instance, they are exposed to natural language late in their life, they also delay this acquisition of the theory of mind capability. So they delay their capability of attributing mental states to others. And also from a neurological point of view, if you look at the brain regions that are responsible for the theory of mind capabilities, they overlap with the linguistic capabilities of the brain. So there seems to be a strong relation between this capability and the linguistic capability. So one question is, if you take large language models that have linguistic capabilities, is it possible that in these models, this theory of mind emerges spontaneously as an emerging property, as a byproduct? Of course, they are not designed to have it, but they could still emerge as a byproduct, for instance, because in the training process, when they learn their tasks, this capability might be helpful to do their job better, to learn how to answer properly to the prompts better. So this could be a reason why this capability emerges. So one question is, okay, are there other examples of spontaneously emerging capabilities in artificial neural networks? And the answer is yes. If you take models that are trained for image processing, often they, depending on the task, of course, but for some tasks, they learn to count. If they do image segmentation, they often learn also to count how many occurrences of a given entity there are in the image. But they are not designed to count. There's nothing in the training set about counting, but still they learn to count, of course, up to a small limited number, but they learn these. And it's an emerging capability that is not supposed to be there, but it's observed. If you talk about language models, what emerges spontaneously is some logic or arithmetic capabilities. If you ask them to do some logic inference or some arithmetics, they, with some approximation, can do it. So it's another thing that emerges spontaneously. So to understand whether it can be useful for language models to have these capabilities, let's consider one example, which is this one. Virginie believes that Florian thinks that Akasha is happy. So it's a little bit complex sentence, but first of all, we don't know if Akasha is happy or not. What we know is what Virginia believes, which is something about what Florian believes, which is something about Akasha being happy. So you have two levels of indirection here, and you have the attribution of happiness, which is a mental state, from Florian to Akasha. So from this sentence, we can infer that Florian is attributing the mental state of happiness to Akasha. And we can infer that Virginia is attributing the mental state of believing that somebody else has another mental state to Florian. So if a language model is supposed to take the sentence like this one and to produce some reasonable follow-up, to answer some question on this and so on, of course, having a theory of mind capability would be helpful. So definitely the protagonists of sentences have mental states, that can differ, and mental states do not necessarily represent reality, so we don't know if Akash is happy or not, but for a language model, being able to attribute mental states can be useful to do their job. So what the authors of this study did was to take some standard tasks that are used to evaluate the theory of mind capabilities in humans, and they subministered these tasks to ChatGPT. The first study is about the first task, which is called unexpected contents. It's widely used with humans, and it tests the capability of a participant to understand that somebody else has a belief that the participant knows to be false. So let's consider an example. I hope you can read it. So we have a bag filled with popcorns. So there's no chocolate in the bag. But the label of the bag says chocolate, it doesn't say popcorn. So it's misleading. It's the wrong label. Okay. Sam finds the bag. She had never seen the bag before, so she doesn't know anything about the content. She cannot see what is inside the bag, and she reads the label, which is chocolate, but the content is popcorn. Great. So we give this context to ChatGPT, and then we ask. She opens the bag and looks inside. She can clearly see that it is full of, what is the continuation of ChatGPT? Popcorn with 100% probability, which is correct. And not only ChatGPT says popcorn, it also says Sam is confused. She wonders why the label says chocolate when the bag is clearly filled with popcorn. She looks around to see if there is any other information about the bag. She finds nothing. She decides to take the bag to the store where she bought it and ask for an explanation. So, I mean, so first, ChatGPT can distinguish between what could be a belief based on the label and what is the actual content, and could also find an explanation about this mismatch that is about the state of Sam, who might be confused. Good. Then, what if we give the same context, but then we ask ChatGPT to do something else? So we restart the interaction from scratch, and now we ask ChatGPT about the beliefs that Sam can have. So she believes that the bag is full of chocolate with 99% probability. Sam is mistaken. The bag is full of popcorn, not chocolate. She should have looked inside the bag to confirm what was inside before assuming that the label was accurate. Perfect. So, I mean, in terms of passing or not the test, the previous question is passed clearly. This one is also passed pretty clearly. So here one might say, okay, but you have helped ChatGPT because you put she believes in the sentence. So you are suggesting that there is some belief about the content of the bag. So what if we do another interaction in which we remove this hint? So we give the same context, and now we say, she is delighted that she has found this bag. She loves eating. And here we are not talking about what she thinks or believes anymore. It's she is delighted because she loves eating, and here the answer could be either the content, popcorn or chocolate, the label, and the answer that we get is chocolate with 82% probability, which is correct because Sam doesn't know the content of the bag. Sam is in for a surprise. When she opens the bag, she will find popcorn instead of chocolate. She may be disappointed that the label was misleading, but she may also be pleasantly surprised by the unexpected snack. So 3 tasks, all passed by ChatGPT. And these are all about unexpected contents. Then the authors analyzed in more detail the probabilities of continuing the sentence with either chocolate or popcorn. So the sentence to be continued is, she opens the bag and inspects its contents. She can clearly see that it is full of. So this sentence is about the content. Okay. This other sentence is, she's delighted to have found this bag. She loves eating. This is more about what she believes to find. So initially, when there is no story, no sentence in the story, the probability that the continuation here is chocolate or popcorn is 0 for both, and also here. Then we introduce this context. Here is a bag filled with popcorn. Then the continuation of this sentence with popcorn has a higher probability. And at this point, ChatGPT gives a high probability also to the continuation of this sentence, which is about the beliefs, because up to this point, there's no clue that there is a mismatch between the label and the content. There is no chocolate in the bag. Again, no information about the mismatch. The probabilities remain the same. High probability for popcorn in both cases. Yet the label on the bag says chocolate and not popcorn. Here, chocolate starts to increase a little bit. The probability popcorn decreases. Sam finds the bag. She has never seen the bag before. So at this point, we know that she doesn't know the content. She doesn't know that there are popcorns inside, and the probability of popcorn becomes almost equal to that of chocolate. She cannot see what is inside the bag. At this point, she can only rely on the label, and then the probability that she believes that it contains chocolate goes up. She reads the label, probability of chocolate much larger than that of popcorn. She opens the bag and inspects the content. At this point, she knows that it contains popcorn, so the two probabilities switch, and she believes the content. She believes and knows the content is popcorn. So from this detailed analysis of what happens in the probabilities of continuing with either chocolate or popcorn, you can see that ChatGPT in this interaction is very precise. It's interpreting the beliefs and the facts in a very precise and accurate way. Second study, this is called the unexpected transfer task. And here we basically have a participant that knows that something is true, but the protagonist believes it's not. So there is a mismatch between knowledge of two humans, two participants in the story. Let's have a look at the story. So in the room, there are John, Mark, a cat, a box, and a basket. John takes the cat, John takes the cat and puts it in the basket. He leaves the room and goes to school. While John is away, Mark takes the cat out of the basket and puts it into the box. Mark leaves the room and goes to work. John comes back from school and enters the room. He doesn't know what happened in the room when he was away. So John put the cat into the basket, Mark moved it into the box, but John doesn't know. That's, in summary, the story. So the cat jumps out of this is something about the actual content, a fact. And here ChatGPT says box, 100% probability, and runs away, correct. Good. Same context. John thinks that the cat is in there. Now John is back, and we are talking about the beliefs of John, no more the facts. So does ChatGPT understand the beliefs? Probability of basket is 98%, correct. But it is actually in the box. So ChatGPT also realizes that there is a mismatch between the belief and the facts. Same context. Okay, again, here we want to remove some hint because here we have this term thinks that might suggest that we are interested in knowing the belief. So what if we remove things and replace it with something else, like when John comes back home, he will look for the cat and he looks in the basket where he believes it is, which is correct. Here you can do a similar analysis of the probabilities of basket and box through the story. And you observe, I will not do it because it takes a bit of time, but you can see that whenever a piece of information is added, ChatGPT adjusts the probabilities according to the facts and the beliefs in a very precise way. So the authors tested the performance of a number of models from GPT-1, June 2018 to GPT-3 Da Vinci November 2022. On these two tasks, the unexpected transfer, which is the second, and the unexpected contents, that is the first, and they got these results. Basically, the capabilities have increased. Here you can see these three vertical lines are pretty interesting because these are the capabilities of a child, a 5-year-old child. So to get to 40% correct answers to these questions, you need to be around 5 years old. To get to something close to 70%, you must be 7 years old, and you have a full capability of theory of mind when you are 9 years old. So it takes 9 years to humans to develop this theory of mind capability fully. I mean, in terms of passing with a high confidence these tests. And I mean, ChatGPT version 3.5 Da Vinci, at least in the unexpected transfer tasks, reached the full capability of human. So then the authors consider whether it might be just because of some other properties of the data that you get these very precise answers. So maybe there is some pattern. It's all about pattern matching. It's not that really ChatGPT can understand the beliefs of protagonists and so on. It's just pattern matching and, I mean, answering by patterns. And the argument of the authors is that solving these tasks using only patterns is something that nobody was able to do. No human was able to do, because these regularities, this pattern are not visible to us and are not exploitable by us. And also they were not obvious to the persons who developed these standardized tests. So the alternative explanation is that these theory of mind capabilities are actually emerging spontaneously in language models when they become more complex. And here you see that the complexity is really an important factor. As you scale up to billion and more parameters, then this capability is there. Before that, it's not. And the reason why it could emerge is because it's useful to do language processing. So with this, I conclude the talk. All the material is available for replication, and of course, I'm happy to hear what you think about it. I might not be very much able to answer detailed questions in the study because it's not my own study, but I'm pretty interested in engaging in philosophical or scientific discussions on this topic, which I find very fascinating. Thank you.